This is our first example of how to use the conservation of energy to solve problems. This is a problem we've done before. We drop a ball off a building, and the building is of some height h or off a cliff or something, and the ball has a mass m, and we want to know how fast is the ball moving just before it hits the ground. All right, we're going to drop it from rest and look at the ball right before it impacts the ground and ask how fast is it moving. Before I solve this with work and energy, let me just remind you of how we solved it with kinematics. With kinematics, we recognize that the initial, this is all in the y direction, I should say, is 0. We recognize that A in the y direction is, let's call down positive. Why not? That lets me write positive g instead of negative g. And it also makes my displacement positive, and we recognize that delta y is equal to h. And once I had those things, then I could go look for an equation to relate all of them together. I probably found this equation: v final squared is equal to v initial squared plus 2a y delta y. All of these are in the y direction, of course. Making the appropriate substitutions. The initial is 0, as I noticed, and the acceleration in the y direction is going to be g. So what I'm going to get here is v final squared is equal to 2g, and delta y is going to be h, 2gh, which means final velocity is root 2gh. That's not terrible. It's not a bad problem to do. It's only, 3 lines long after thinking about it. We're going to do it with conservation of energy now, and we're probably going to find out that in this case, it's not really that much less work to do it with conservation of energy, but there are certainly a lot of cases in which energy is easier. But I'm just doing this to remind you of what we know, and also to give us a check on our answer, because we know what the answer is. We found this before. All right, so if I'm going to do this with conservation of energy, it's probably good to write down the equation of conservation of energy. To begin with, initial kinetic plus initial potential plus work due to non-conservative forces is then equal to kinetic final plus potential final. And on the face of it, I've got a lot of terms here, and you might be going, how is this easier? Well, it becomes easier if we do some clever setting of our 0 point. So if I set my 0 point at the bottom, my 0 point for potential energy, I should say, and that makes sense. That's where I've set my origin in my first system anyway, right? When I said delta y is equal to h, I set my origin here. So if my origin is here, this is my 0 point for potential energy. That means when the ball gets to this point, I get an expression of, potential energy here is equal to mg times 0 meters. Well, that gives me exactly 0 meters, or 0 joules, right? So if I set my 0 point here, my final potential becomes 0. Do I have to do that? Absolutely not. I can set it anywhere I want to. I'm going to get the same answer. It's just that it's less work if I do this. So I do this because physicists are inherently lazy. Fair enough. Okay, next thing. Well, if I'm ignoring air resistance and there's no friction here, then I don't see any good candidate for a non-conservative force. In fact, the only thing I have acting here is gravity if I'm ignoring air resistance. And so gravity is conservative. So in this case, there is no work done to non-conservative forces. That goes away, and, well, lo and behold, I'm dropping the ball from rest, right? My V initial is 0. If my V initial is 0, then therefore 1/2 m V initial squared is 0, and that turns out to be 0. So this is looking better and better, right? We like getting rid of things. You won't always be able to get rid of these, but in this case you can, and so what I get now is this really simple expression involving initial potential energy and final kinetic energy. I just make the substitutions. Initial kinetic energy is mg times the distance from my 0 point, which is h. I get mgh is equal to final kinetic energy. That's 1/2 mv final squared, right? And that's good because that's what I'm looking for. I've got an m in both sides. That's going to go away. It looks like I'm going to multiply both sides by 2 and take a square root. So I get v final is equal to root 2gh, just like I got there. Now, again, three-line problem. I don't know that I really gained anything in solving it with work and energy, but there are lots of problems that I'm going to be able to solve a lot easier with work and or energy than I can with kinematics. And we're going to see some of those in the next few videos. But for now, I just want to remind you, or I just want to show you that this works. It works very nicely, and we already know the answer, so we can check ourselves. And that worked out really well. Notice how the m's go away here. You're going to see that a lot. Of course, when we start dealing with springs, they don't have a mass in their formula, so we won't see this. But if you're dealing with gravitational potential energy, because that involves the mass, and the kinetic energy involves the mass, we're going to see these go away quite a bit. It's actually quite lovely.